All right, if you're getting ready for a software engineering interview, you know there's one question that comes up all the time. It's the big one. What happens when you type a URL into your browser and hit enter? Now, interviewers don't ask this to be tricky. They ask it because the answer touches on, well, pretty much everything. It shows you if you really get the whole tech stack. So today, we're going to crack this thing wide open and follow the entire journey step by step. Let's get into it. So this is it, the classic question. And the best way to answer it is to tell a story. We're going to follow one single tiny data packet on its wild ride from your computer out across the entire internet to a server and all the way back home. By the time we're done, you'll be able to walk an interviewer through every single twist and turn with total confidence.
Okay, so our story starts right where you'd expect, with you, in your browser. This is what we call the application layer. You can think of all network communication as kind of like a four-layer cake, and this is the very top layer. It's where your browser lives, and it's the place where your simple action, typing in a web address, gets translated into a real request that the network can actually understand.
So, before your browser can send anything, it needs an address, a real address. See, computers don't understand names like Google.com. They only speak in numbers, specifically IP addresses. So the very first thing that has to happen is a DNS lookup. Your computer is surprisingly resourceful here. First, it checks its own little memory, its cache, to see if it's been there recently. No? It asks your operating system. Still no? It checks your router. If nobody knows, it finally goes out to a DNS server on the internet. It's literally like looking up a name in the internet's giant phone book to get the right number.
Awesome, we've got the IP address. Now your browser knows exactly where to send the message. And the message itself? It's written in a language called HTTP. Or more likely these days, it's Secure Twin, HTTPS. This is the official language that browsers and web servers use to chat. Your browser sends what's called an HTTP GET request. It basically says, hey, can you please send me the content for your homepage? And it also includes some extra info like what browser you're using, just to be helpful.
So we have our message and we have the destination address, but you can't just, toss it out onto the internet and hope for the best. It needs to be properly packaged for the journey. This happens at the next layer down, the transport layer. And here we have to make a choice. We have to pick a shipping service. The two main options are TCP and UDP.
Think about loading a web page. You need every single piece of it, right? Every image, every line of code. If even one little packet goes missing, the whole page could be a garbled mess. That's why, for this job, we use TCP. It is the white glove, guaranteed delivery service of the internet. It makes absolutely sure every single packet arrives safely in the right order. Now, how does TCP make that guarantee? It doesn't send any data until it establishes a solid connection using something called a three-way handshake. It's like a quick phone call. Your computer sends a SYN packet, which is like saying, hey, you there? The server replies with a SYN-ACK, which means, yep, I'm here and I hear you. Finally, your computer sends one last ACK saying, great, I hear you too, let's talk. Now the connection is stable and they can start sending the actual web page data back and forth reliably.
But what if you don't need perfect reliability? What if you need speed? Imagine you're on a video call or playing an online game. If one tiny piece of video data gets dropped, you might see a flicker for a millisecond. You probably wouldn't even notice. But a delay, a lag, that's super frustrating. That's where UDP shines. It's a fire and forget protocol. It just sends the data as fast as it can. No handshake, no error checking. It's way faster, but with no guarantee of delivery. And let me tell you, understanding this trade-off right here is absolutely critical for any technical interview. TCP is for reliability. Think websites, file transfers, anything where you need every single bit to be perfect. UDP is for speed. Think live video, online games, voice calls, anything where it's better to miss a little data than to wait for it. Knowing when to use which is a huge green flag for an interviewer. One last crucial piece at this layer. When our packet gets to the server, that server is probably running dozens of different services. How does it know our packet is for the web server and not, say, the email server? The answer is ports. Think of the IP address as the street address of a huge apartment building. The port number is the specific apartment number. Our HTTP request is aimed at port 80. A secure HTTPS request goes to port 443. This tells the server exactly which application should get the data. And that combination, an IP address plus a port number, is called a socket. Remember that term. Okay, our data is now neatly packaged up. It moves down to the next layer, the network layer. And here, it gets wrapped in another layer of information.
This is called encapsulation. It's literally like taking our package data and putting it inside a shipping envelope. This new envelope is now an IP packet, and it gets stamped with the sender's and receiver's global IP addresses. The address on that envelope is, of course, the IP address we got from our DNS lookup earlier. This is the unique mailing address for that server anywhere in the world. Now, you'll mostly see IPv4 addresses. Those are the 4 numbers separated by dots we're all used to. But because we're running out of those, the world is slowly but surely shifting over to the much, much larger IPv6 address space to handle all the new devices coming online. Now, here's the concept that can be a little tricky, but it's super important. At home, your laptop, your phone, your smart TV, they all have their own private IP addresses. But to the outside world, your entire house shares just one single public IP address. How is that possible? Well, your home router is a clever little device. It uses something called Network Address Translation, or NAT. It acts like a receptionist. When a packet leaves your laptop, the router swaps out your laptop's private address for its own public one. It also keeps a little note of who sent what. When the reply comes back, the router checks its notes and forwards the packet to the correct device. It's an ingenious system that helps us not run out of IP addresses.
So, the internet isn't one straight road. It's this massive, tangled web of connections. How on earth does our packet find its way? That's the job of routers. You can think of routers as the traffic cops of the internet, and they use routing protocols as their GPS. These are complex algorithms that are constantly talking to each other, sharing updates about traffic and network changes, all to calculate the absolute fastest, most efficient path for your packet to take to its destination at that exact moment. Our packet has navigated the maze of the internet. It's so close. It has finally arrived at the local network where the web server lives. But the journey isn't quite over. We now drop down to the final layer for this trip, the data link layer, which handles this last critical hop from the local router to the specific server machine.
Okay, this is another key distinction you need to nail for an interview. An IP address is a logical address. It's like your home address, and it can change if you move. But every single network device, your laptop, a server, has a permanent, physical MAC address that's burned into its hardware from the factory. It never changes. It's like the device's unique serial number. The IP address gets the packet to the right building, the MAC address gets it to the right apartment. So, the local router has a packet for a specific IP address, but it needs to know which physical machine to hand it to. How does it find out? It uses a protocol called ARP. The router basically just shouts out to everyone on the local network, "Hey, I've got a packet for this IP address. If that's you, please tell me your MAC address." The server with that IP address hears the call and replies with its MAC address. The router then delivers the packet, and to be efficient, it saves that IP to MAC mapping in a little table so it doesn't have to ask again next time. And this final hop really brings a key performance metric into focus: transmission delay. This formula here just tells you how long it physically takes to push all the bits of your packet onto the network cable or through the Wi-Fi. But remember, this is just one piece of the puzzle. The total time it takes for a packet to get somewhere, its latency, also includes how long it takes to travel the physical distance, that's propagation delay, and any time it spends waiting in line at busy routers, which is queuing delay. Knowing all these factors is how you really start to diagnose network slowdowns. Okay, our packet is just about to be delivered. But wait, we've been sending this data across the public internet. That's kind of like shouting your private information in a massive, crowded room. Anyone could be listening in. That's why we almost never use plain old HTTP anymore. We use HTTPS, and that S for secure is maybe the most important letter in the whole address. Let's see how it works. The magic behind that S is a protocol called TLS. It gives us 3 incredibly important security guarantees. First is encryption. It scrambles the data, creating a private tunnel so that even if someone intercepts our packet, it's just unreadable garbage to them. Second is authentication. It uses digital certificates to prove that the server we're talking to is actually Google.com and not some imposter. And third is integrity. It makes sure that the data hasn't been secretly changed or tampered with on its journey.
Now, TLS does this in a really clever way by combining 2 different types of cryptography. First, it uses slow but super secure asymmetric cryptography, that's the public and private key stuff, just for the initial handshake. The whole point of this is for the browser and server to safely agree on a secret key for this one conversation. Once they have that shared key, they switch to much faster symmetric cryptography to encrypt all the actual data. It's the best of both worlds: maximum security for the setup and maximum speed for the actual communication.
So, the journey we've just followed is the happy path. It's how things are supposed to work. But in the real world, well, things break. Networks go down. A huge part of being a great engineer is being a great detective, knowing how to figure out what, where, and why something went wrong. So let's wrap this up with the essential tools you'll need in your toolkit.
These 4 command line tools are your absolute best friends for network debugging. Ping is the simplest. It just answers the question, "Are you there?" and tells you how long it took to get a reply. Traceroute is amazing. It shows you every single router your packet hops through on its way to the destination, so you can see exactly where a slowdown or failure is happening. And SLOOKUP lets you check if DNS is working correctly. And Netstat gives you a peek under the hood of your own machine to see all the network connections it currently has open. You've got to know these.
And there you have it, the complete journey of a single packet. From an application request, wrapped in layer after layer, routed across the globe, and delivered securely. Every protocol makes a choice. Every layer has a job. Understanding this journey is the foundation. But to really ace that system design interview, you have to think bigger. How do these ideas scale? How do you use things like load balancers and content delivery networks, or CDNs, to handle not just one request, but billions of them all at once? That's the next level. And now you have the building blocks to start answering it.